electrons had some kind of wave behavior. Namely, if they were following these circular path orbits, then an orbit of a specific diameter, okay, and a specific circumference would only have certain allowable standing waves that could be created. And these certain allowable standing waves could account for there being only certain allowable energies. So he's going to propose that matter, all matter, has some kind of wave behavior. That moving particles have a wave behavior. Okay? And being a good physicist, he has to have a mathematical equation. And his equation is lambda equals h over mu. Lambda is the wavelength, h is Planck's constant, m is mass in kilograms, and u is velocity in meters per second. I think your book actually uses a lowercase v, so you might see it written h over mv, v for velocity. Okay, so notice, the faster something is moving, the smaller its wavelength is going to be. The larger the mass something is, the smaller its wavelength is going to be. Okay? What this is kind of leading us toward is up here in the world of large objects. Even something as small as my piece of chalk. Okay? The wavelength is going to be so small compared to the size of the object that it's negligible. We don't see it. But when we get down to the size of an electron, where the mass is very, 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 very tiny, and its diameter is very, 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 very tiny, the wavelength becomes so large compared to the size of the object that it becomes important. Okay? So all matter that's moving, according to de Broglie, has a wave behavior, but only when we get down into the world of the very small does that wave behavior become important. Now, you're going to make a claim like this, you're going to have people test it. And what they did is they took and they shot an electron beam at slits to look for an interference pattern on the other side, like we saw with light hitting slits. And lo and behold, they saw the interference pattern. So the electrons showed wave behavior. Okay? So let's look at problem 2.4 on page 90. We'll do a quick calculation, and then we're going to talk about uncertainty. Okay? Now, if we look at 2.4, it says, what is the velocity of the electron that has a de Broglie wavelength, approximately like wavelength of a chemistry bond, 1.2 times 10 to the minus 10. So we're told that lambda is 1.2 times 10 to the minus 10, and we're asked to calculate the velocity. And that should be in meters per second, and this would be in meters. Okay, so we're going to use the de Broglie equation, and in the de Broglie equation we have lambda equal h over mv. So if I rearrange this, v is going to equal h over m lambda. So we got 6.626 times 10 to the minus 34. Now, when de Broglie was using Planck's constant, there's an alternate set of units, and he used the units kilograms meters squared over seconds. Okay, the mass of an electron, electrons are very tiny, and we want the mass in kilograms. The mass of an electron is 9.11 times 10 to the minus 31 kilograms. Don't panic, that's not something you have to memorize. It is a value that's found in the back cover of your textbook, Fundamental Constants. Okay, on an exam where you were working problems for me, I would give it to you. 1.2 times 10 to the minus 10 meters is the wavelength. So notice kilograms are going to divide out. One of the meters are going to divide out. And we're just going to be left in units of meters per second. So let's calculate. 6.626 EXP 34 negative divided by 9.11 EXP 31. I get my answer. And then I'm going to divide by 1.2 EXP 10 negative. And I get 6.06. Well, actually that has 2, so I'm going to go 6.1 times 10 to the 6 meters per second. That electron is hollow. It's moving. Okay? Don't be surprised by really large numbers like this. When we're calculating speeds of electrons, they're quite often very large numbers. Okay? So that's how we're going to calculate the velocity of electrons. Now, what we have to start thinking about, if we're going to start thinking about electrons as a wave, and the wave and particle nature of electron, because we can see both, we have to start thinking about uncertainty. Okay? So people are looking at de Broglie's approach to the electron and its wave nature. And we know that under certain situations, electrons act like a particle. Under other situations now, we're predicting that electrons act like a wave. So we can do the double slit experiment with the electron. Okay? And so let's look at the following. Now, let's look at it on my screen. Wait, you're traveling, you're looking at my screen. All right, now, we know that when we pass electrons, okay, or light through double slits, we get a diffraction pattern. If we were to do the same thing with light BBs, we'd actually only see 2 lines. We wouldn't see a diffraction pattern because particles don't interfere with each other. If they hit each other, they bounce off each other. But I should have 2 straight beams of particles. Okay? So now comes the tricky part. We're going to do that double slit experiment with the electron, and we're going to put a laser beam right beyond the slit so that the laser beam interacts with the electrons as they come through the slits. The minute that you turn the laser beam on so that you can detect what slit an electron passes through, the diffraction pattern goes away. The minute you turn the laser beam off, you get the diffraction pattern again. What this tells us is when we get down to something as tiny as the electron, our attempts to determine what it's doing actually disturbs the system so that it changes the outcome of our experiment. If we look to see which slit the electron is passing through, we get rid of the inference pattern. If we don't try to detect which slit the electron goes through, we get a diffraction pattern. So here's the rub. Okay? It turns out that no matter how hard we try, no matter what method we use, okay, we can never see both the wave behavior and the particle behavior of an electron at the same time. Let me say that again. No matter how hard we try, no matter what we do, There is a limit to our ability to make measurements. We can never see the electron behavior as a particle and the electron behavior as a wave at the same time. We are going to have to look either at the particle behavior or at the wave behavior, but we can't do both at the same time. And the electron displays both behaviors. So there's an inherent in nature a limit to our ability to detect. Okay? We talk about the wave behavior and the particle behavior of nature as being complementary, which excludes one another. The more we know about the wave behavior of an electron, the less we're going to know about its particle behavior. The more we know about its particle behavior, the less we're going to know about its wave behavior. So scientists were at a conundrum. They were at a breaking point. Okay? How are we then going to study and understand the electron? And we know that we're dealing with very small objects, and truthfully we're going to deal with huge numbers of objects at a time. And Heisenberg was a German scientist who was looking at this, de Broglie, Planck, Einstein's ideas, Rutherford's ideas, and he said, you know what? There's just always going to be some uncertainty inherent in our study of the electron. And he came up with the uncertainty principle. This is Heisenberg. Heisenberg, good German name. Now, the Heisenberg uncertainty principle says that the more we know about the position of the particle, the less we know about the speed. Or vice versa. The more we know about the position, the less we know about the speed of the particle. Okay? Now, Heisenberg is a physicist. That means there's an equation on our horizon. It says that delta x times m delta v has to be greater than or equal to h over 4 pi. Delta x is our uncertainty in position, m is mass, delta v is uncertainty in speed, h is Planck's constant, and of course pi is 3.14159. Okay? So let's say that I had an electron. So we were given an electron. Mass is 9.11 times 10 to the minus 31 kilograms. And its uncertainty in its speed is 3.2 times 10 to the 1 meters per second. So that's 32 meters per second. That would be a very small uncertainty in the speed of an electron. And I wanted to know what the uncertainty in position is. All I have to do is plug into the equation. Delta x times the mass, 9.11 times 10 to the minus 31 kilograms, times the uncertainty in speed, 3.2 times 10 to the 1 meters per second, has to be greater than or equal to 6.626 times 10 to the minus 34 kilograms meters squared over seconds over 4 times 3.14159. So 6.626 exp 34 negative divided by 4 divided by pi divided by 9.11 exp 31 negative divided by 3.2 exp1 says that my delta x is greater than or equal to 1.71 times 10 to the minus 6 meters. That's much larger than the diameter of an atom, the smallest atom, hydrogen. So even with that small an uncertainty in speed, we've got a giant uncertainty in position compared to the size of an atom. Okay? Make sure you got it. Whee! Okay, now this is where Einstein got off the bus. He had a knockdown, drag out with Heisenberg. Kind of a paraphrase of something Einstein said was that God doesn't play dice with the universe. He believed that we should be able to know everything, exact position and exact velocity at an instant in time. And Heisenberg is saying, not within our ability to measure, we're not. There is always going to be uncertainty, either in position or velocity, or really both. Okay? Now, this brings us to deterministics versus probability. Classical physics works on deterministics, where the present determines the future. So if you think about hitting a baseball, if you know exactly where the batter hits the baseball, okay, and what angle and what energy they put into it, you can plot a trajectory and determine approximately where the baseball lands. You think about firing a cannon. We know that at this angle with this much charge, the cannon's going to follow this pathway and it's going to land here. Boom! Okay? That's different than probability. Probability says if I launch this electron from this location, it'll end up somewhere in here. Okay? It gives you a smear. So if we plot out where something is going to go, probability looks quite different from deterministics. Okay? Now in your notes, pretty picture, okay? Deterministics, a nice straight line pathway. Quantum mechanics, notice it's all this fuzzy. The electron taking off from here as it goes along the way could be any one of those locations, and it doesn't land in one spot. It could land in a multiple places at the end. Okay? So if we think back to Victorian times, the late 1800s, okay, when they were starting to think about probability, we could say you can't have your cake and eat it too. You can't know everything there is to know about an electron when it comes to position and velocity. All right? And this is a good stopping spot, so that's where we'll stop.